This is the first episode in a series where I'll be talking through my undergraduate philosophy thesis. My main goal in the paper is to draw some connections between a view called realist structuralism in the philosophy of mathematics and the new area of metaphysics called higher order metaphysics. These areas of philosophy are known for having a rather high barrier of entry, and for good reason. However, in this series, I hope to break down all the concepts and start from the beginning. No prior knowledge about the philosophy of mathematics, the metaphysics of abstract objects, or set theory required. I'll walk through each important concept of the paper slowly and individually, and I hope to motivate each part both historically and intuitively. Also, since I'll be going through each part slowly, I hope to pull on some interesting and important threads that come about from our journey together that might not be relevant to my ultimate project. So, even if you're just interested in the philosophy of math or higher order metaphysics, this series will hopefully serve as an easy introduction. In this first episode, we'll start off with the philosophy of mathematics. My goal today is just to try to motivate the view I talk about in my paper, which is called Structuralism. But to do that, we'll need to dip a little bit into the foundations of mathematics. Study of the foundations of mathematics really began with the philosopher and mathematician Gottlob Frege in the late 1800s and early 1900s, who was building off the work of Georg Cantor a decade or so earlier. It is difficult to understate the importance of these two figures, especially Frege, when talking about the philosophy of mathematics. Realistically, the tools to study the foundations and philosophy of mathematics didn't exist before Cantor, and without Frege, we would lack the rich philosophical insights Cantor's tools are capable of uncovering. Cantor's main contribution was the development of set theory, which is the formal study of collections or sets. A good question to ask is, why might we be interested in studying sets at all? One way to motivate set theory is by starting to ask questions about different collections of numbers. Consider the set of natural numbers, or counting numbers. By the way, this is a set we'll keep coming back to again and again. The set of natural numbers contains 0, 1, 2, 3, and so on. From this set, we can pull out just the even numbers, 0, 2, 4, and so on. We could also pull out just the odd numbers, 1, 3, 5, and so on. Let's ask the question, are there more even numbers or odd numbers? Certainly, we can't pin down just one number as both sets go on continuously. But it seems like that these two sets have the same number of numbers. For each even number, I can add 1 and get every odd number, and for each odd number, I could subtract 1 and get every even number. Despite going on forever, the sets have some special correspondence with each other. But now let's ask, is the set of all natural numbers bigger than these two sets? Intuitively, the answer is yes. There's just more natural numbers per even or odd number. However, we can still get the same kind of correspondence between the naturals and the evens or the odds. Take any natural number and multiply it by 2 and you've got all the even numbers. Add 1 to that number and now you've got all the odd numbers. So the naturals are the same size as the evens and the odds? Even though there's always more natural numbers per even or odd number? It's easy to get lost here and difficult to tell exactly what is going on. The problem is, this is just the start. The natural numbers are fairly well behaved. Things get really strange when we move out of the natural numbers. So we probably want some way to capture both that special correspondence we noticed, but also the fact that there are more natural numbers per even or odd number. In other words, we want some way to study infinity a little more carefully. To do that, we need to look at sets like the natural numbers and see what properties about its size come about from it. Frege takes set theory on board and notices that, given the highly general nature of sets, we can take some initial stabs at trying to pin down the foundations of mathematics. A natural place to start is by cashing out this idea of number. Back in ancient times, Plato thought numbers were a kind of perfection that lived up in philosophical heaven. In other words, according to Plato, numbers are real things somewhere in the universe that can interact in special ways with us and the objects around us, and which we can learn about by philosophical inquiry. We'll try out Plato's ideas for our philosophical starting points, and we'll try to tweak his ideas a little bit and put some set theoretic flesh and bones on the core idea he's trying to get at. Let's first notice that, while we don't interact directly with numbers as we do with normal objects, we learn about them and can deal with them indirectly through quantity. I don't just think hard enough and learn what 5 is or means, but rather I learn about 5 through quantities of 5 things. For example, say I've got this pile of apples and another pile of oranges. It's pretty easy to see that there's something in common about these two piles, namely the quantity of apples is the same as the quantity of oranges. In this case, I'll call this special property that both piles have 5. So I'll gather together all the piles that have the property of 5 into a set and call that big set with every pile that has 5 elements in it the number 5. In other words, the number n is the set of sets with n elements in it. From here, now that we've defined numbers with sets, we can build up arithmetic using relations between those sets. Furthermore, we can use everything we learned in set theory to mess around with these sets and see what happens to anything we've built on top of them, like numbers and arithmetic. I won't go into the details here, but as we can see, using sets in this way makes the foundations of mathematics really nice and cohesive. We're not building up mathematics from some weird place or unintuitive first principles, but rather from the very general and intuitive idea of sets. Now, as a side note, I'm glossing over a lot of technical details. I won't try to explain everything, but I'll mention a couple of things here in case you decide to go read Frege for yourself. Frege didn't really talk about sets. Rather, he talked about extensions and concepts. Concepts are like properties which an object may or may not have, or may or may not fall under. And extensions are like sets of objects that satisfy some concept. Numbers are extensions of concepts for Frege, so they're sets of objects that satisfy a particular concept. All that aside, it's easy to see how attractive set theory is to form the foundations of mathematics. As study progressed in the foundations of mathematics, people discovered that there are actually a number of different ways to define the natural numbers, depending on the set theoretic properties we're interested in exploiting. Frege's definition of number is fairly restrictive and doesn't give us too many things to work with. For instance, each set that corresponds to a natural number, except for 0, is infinitely large. An early set theorist, Ernst Zermelo, suggested the following. We let 0 be the empty set, the set that doesn't contain anything. Then 1 is the set of the empty set, 2 is the set of 1, or the set of the empty set, 3 is the set of 2, or the set of the set of the set of the empty set, and so on. On this construction, we can build relations between those sets that look a lot like addition and multiplication, and so build up arithmetic from this definition as well. John von Neumann, a later mathematician and set theorist, has a more complex construction. 0 is the empty set, 1 is the set containing both the empty set and the set of the empty set, 2 is the set containing the empty set, the set of the empty set, and the set containing the empty set and the set of the empty set, and so on. In other words, 1 contains 0, 2 contains 0 and 1, 3 contains 0, 1, and 2, and so on. There are lots of nice properties of this construction, so they get a special name called the ordinals, or the von Neumann ordinals. The reason why we can define numbers in lots of different ways can get a bit technical, but it'll be worth it to dwell on it for a little while as it'll be important moving forward. Let's start by asking the question, what does it mean for a system of objects to build up arithmetic? To answer this question, we need to introduce the formal notions of theories and axioms. Moving forward, I'll use the word theory to mean a set of sentences. Axioms are a few sentences of a theory that have the special property that every other sentence in that language can be derived from them using formal logic. Since axioms and theories are sentences, we need to specify a language with which they are constructed. It is important to note that we have to reorient a lot of the way we think about mathematics when we bring in theories, axioms, and languages into the discussion. The first thing we need to do to reorient our thinking is to basically completely gut mathematics of any substance. When we see the 1, don't think that this actually refers to anything. Instead, just look at it and see it as a symbol and nothing else. When you see the plus sign, don't think that this tells us anything about how numbers relate. Just see it as a symbol. This holds for whole expressions as well. 1 plus 1 equals 2 is just an ordered string of symbols, and it doesn't tell us anything about the way the world is or how numbers work. Thinking this way completely guts mathematics. In fact, since we haven't even specified what truth is in mathematics, we can't even say what it means for a sentence to be true yet. The reason we do this is because we want to have control over what exactly these symbols tell us. Later on down the line, we'll specify how we want to understand these symbols, and that'll allow us to start adding substance back into mathematical talk. But until we do that, as far as we're concerned, mathematics is nothing more than just sets of sentences. The idea is that the theories or sets of sentences we're interested in are the ones which are used in mathematics. So the theory of arithmetic is a set of all sentences of arithmetic we want to eventually be true. So we want 1 plus 1 equals 2 to be in our theory, as well as 2 times 2 equals 4 and 3 is less than 5, and all the other arithmetic truths. Next, we want to find a handful of sentences that, using logic, we can get all of the sentences in our theories. This set of sentences will be our axioms of arithmetic. Finding the right axioms is not easy, so I won't go through how we do it. Axioms also tend to be pretty technical, so I won't go into detail about what they mean, but the axioms of arithmetic get a special name. They're called the Peano axioms, or PA, named after Giuseppe Peano, who first discovered them. The Peano axioms tell us all the properties of the equal sign, how to generate all and only all the natural numbers once we've got our zero, and how addition and multiplication work. It is important to keep our reorientation in mind. Logic gives us rules to rearrange symbols, and the Peano axioms are just sentences such that, when we rearrange the symbols of the Peano axioms according to the rules of logic, we can get all the strings of symbols in our theory of arithmetic. Since there are only a handful of rules for logic, and the Peano axioms are easy to list out, we can state everything in our theory just by stating what our language is, what the Peano axioms are, and what logic we're working with. Since everything we're doing is in classical logic and the language of mathematics, it's redundant to keep stating we're in the language of math and classical logic. So, in fact, we can just talk about mathematical theories just by their axioms. This is a much better and easier way of building up theories than just listing out everything that we want to be true. Since everything going on here is just rearranging symbols and strings of symbols, we call all of this syntactic, which refers to the fact that all we care about right now is ordering and arranging symbols. Syntax is opposed to semantics, which tells us what symbols mean and what makes a string of symbols true. Now that we've got our axioms for arithmetic, we can move on to figuring out the semantics. The basic idea is that we'll first take a big collection of objects. Then we'll try to line up objects to symbols in the language of the axioms we're interested in, and ways of rearranging the symbols in the language with different operations and relations on the objects. We'll have succeeded in providing semantics for arithmetic when we find a way to do all that for a collection of objects in a way that every sentence in the theory of arithmetic lines up with the correct way that the objects relate to each other. Once we do that, we'll call the collection of objects and way to line them up with the language a model for the Peano axioms. Alright, now all this is pretty abstract, but I'll try to illustrate using the collection or set of sets that look like the empty set, the set of the empty set, the set of the set of the empty set, and so on. And this is just the set of Zermelo's definition I mentioned earlier. This set will serve as our set of all the numbers. The first thing to do is to get our zero. The easiest thing to do is line up the zero symbol with the empty set. Next, we need to find a relation on all these sets that has the same properties as equality in arithmetic. Set theory has its own way of doing identity. A set A is identical with a set B if and only if they have exactly the same elements. So we don't need to do anything except adopt that definition of identity for our numbers. Next, we need to specify how we'll generate all the natural numbers. The way we do this is by lining up the set with n brackets around the empty set with that corresponding symbol in our language. So we line up the set of the empty set with 1, the set of the empty set with 2, and so on. In essence, to go up the natural numbers, we add more brackets. To go back down, we take away brackets. We can define addition by saying a plus b is the result of taking all the brackets around a and putting them around b. We can define multiplication by saying a times b is a result of adding all the brackets around a to every bracket around b. Finally, we can define the less than relation by saying a is less than b is true whenever it's possible to add brackets around a to get b. Given Zermelo's definition of numbers, and lining up these sets with the symbols and these operations on those sets with the arithmetic operations in this way, gives us a model of arithmetic. The key insight here is that there are, in fact, infinitely many models of arithmetic. The von Neumann ordinals I mentioned earlier is a model of arithmetic, and so is Frege's definition of number, and even any random collection of objects you might have lying around. The fact that there are infinitely many models of arithmetic was known pretty early on. But in the early 1960s, a philosopher at Princeton named Paul Benazaraf wrote a couple of classic papers that defined how modern philosophy of mathematics would be done. The one of interest to us is called what numbers could not be. Benacerraf asked, what are numbers? Most people think, for good reason, that at the bottom, mathematics is just about sets. So numbers are sets. But Benacerraf keeps pressing and asks, which set of sets are the numbers? The von Neumann ordinals are the canonical way of defining the numbers. However, Benacerraf notes that just to do arithmetic and define what makes a sentence of arithmetic true, the Zermelo definition of numbers works just as well. This is just because the Zermelo numbers are also a model of arithmetic, so they make every sentence of arithmetic true. How do we tell what's a number, then? The von Neumann ordinals and the Zermelo sets give us two perfectly good ways of defining truth in arithmetic, so there doesn't seem to be anything that makes one better than the other, and so there doesn't seem to be anything that tells us what exactly a number is. Benacerraf's key insight is that we don't really care about what numbers are. Rather, what we care about are things that model arithmetic. In other words, we're interested in collections of objects with some operations on them that have the same structure as arithmetic. A collection of objects with the right operations on them models arithmetic because of some special property about those objects and operations. We call that special property the structure of those objects with those relations. A collection of objects with some operations has the same structure as arithmetic when that collection with those operations models arithmetic. This gives us our first motivation and first pass at structuralism in the philosophy of mathematics. Structuralism is the view that mathematics studies and is interested in these special properties, or structures, that make a collection of objects with relations model arithmetic, or any other theory of mathematics. This is distinct from older views about mathematics. For instance, according to Plato, mathematics is the study of numbers and what they really are. Frege thought mathematics is the study of logic, and early set theorists thought mathematics is the study of sets. Structuralism, on the other hand, thinks mathematics is interested in special collections of relations or structures, which, when a collection of objects exemplifies those relations or structures, makes those objects model a theory of mathematics. So, hopefully by now, you can see how beginning with set theory and the first attempts to pin down what numbers are in the early 1900s eventually gives rise and motivates a rudimentary form of structuralism. There's still so much to talk about when it comes to structuralism. Do structures exist? How many are there? How does a collection of objects exemplify a structure? How do we know about structures? And the questions continue to abound. But we'll have to answer these questions in the next episode. For now, thank you so much for watching.